Welcome back to this course on polymer chemistry, and today's lecture we will continue our discussion we are having on amorphous and crystalline state, and we will have discussion on glass transition temperature and melting point of polymers. Now, if you look at this slide, this is the topic, these are the topics we thought of covering in this amorphous and crystalline state. We have covered in last lecture our introductory discussion on amorphous and crystalline polymers, and then we discussed what is glass transition temperature and melting temperature for polymers. We discussed that glass transition temperature is a secondary transition, glass transition is a secondary transition, and melting is a first order transitions for polymers. We also discussed in detail about the relationship between chemical structure and glass transition temperature, and in today's lecture we are going to discuss the relationship between the chemical structure of a polymer and the melting point. We will discuss today about how the measurement techniques used for Tg and Tm. We will not have detailed discussion, but the basic discussion, basic technique on determining Tg and Tm. And we will also discuss a little bit about other thermal responses, other responses polymer shows when you heat up a polymer material. Just to recap, the factors which that influence glass transition temperature, mainly we can divide in two factors. One is free volume. Free volume is the volume in a polymer material which is not covered by the polymer molecules, and as we have seen that if we increase the free volume content in a polymeric material or sample, the polymers has more space to move around, so mobility goes up, and hence the effect of it affects the glass transition temperature, and we will also see that it affects the melting point. Second major or the main contribution in determining factor in Tg is the freedom of the polymer chain to rotate around its single bond, which gives us the mobility of the polymer chain. So, if you increase the mobility, obviously polymer chains become more flexible and Tg goes down. So, if you go back and look at these factors we discussed in last lecture, if you have a rigid backbone, rigid group in the backbone, then Tg goes up as a result of increased stiffness. Flexible backbone, obviously Tg goes down. If you have the steric hindrance because of presence of bulky side groups or bulky pendant groups, then the rotation around single bond becomes difficult. As a result, stiffness goes up and Tg goes up. If you have long plasticizing side group, then obviously free volume goes up and Tg goes down. Similarly, symmetrical substituents we have seen that Tg brings down. Polar functionalities will increase the intermolecular or interpolymer attractions, which will increase the Tg. Plasticizers increase the free volume, Tg goes down, and cross linking also decreases the amount of free volume, so Tg goes up. Now, these are some of the factors we tried to include, and we will see that most of these factors also influence the value of Tm, because Tm and Tg we will see are very closely related phenomena. So, these factors also will contribute, may not be in same extent or same nature, same way, but they also contribute in determining value of the glass transition temperature. What about the Tg of copolymer? We talked about mainly in the last class Tg of homopolymers. Now, what about the Tg of copolymers and polymer blends? If you talk about copolymers first, now copolymers you can have random copolymers. Now, if you have random copolymers, obviously they form a single phase, because the individual monomers does not make a they are not distinct to each other in the sense that they are statistical copolymers. So, you have a single phase for that, and if you have a single phase, this gives us a single Tg for the copolymer. If you have block copolymer, now if the blocks involved here are immiscible with each other, then you have multiple phases. For example, if we are talking about two blocks, then if they are not miscible with each other or other way immiscible to each other, then we have two phases, then we have multiple Tg's. Each Tg represents the Tg for the corresponding homopolymer. So, if you have two blocks which are not miscible, then we are going to get two Tg's for the corresponding homopolymer. Now, if please remember that if this Tg, the Tg of the homopolymer in a block copolymer will depend upon the size or the molecular weight of copolymer, as we know that the Tg also depends on the molecular weight of the polymers. So, if we talk about the small block, then we are going to get slightly less Tg than a large homopolymer. So, that part you have to keep in mind, that if you take a small block, then Tg will be lower comparative to a homopolymer which have a higher molecular weight. These copolymers, the two blocks are miscible, then obviously you are going to get a single phase, and which will give us a single Tg. Similarly, if we take two homopolymers and blend them, if we have immiscible, again similar thing, then you have immiscible multiple phases, multiple Tg's. If you are talking about say two homopolymer blend, so multiple Tg. If they are miscible, obviously single phase, and you have single Tg. For immiscible blend, it does not matter, you know the Tg's for the homopolymers, obviously then you will know the Tg's for the block copolymer, immiscible block copolymer or immiscible blends. What is the Tg for a miscible blend? If you mix say component 1 and component 2 and then mix with each other, or you make a block copolymer of 1 and 2 which becomes miscible, then what is the Tg? Now, there are two equations which you can apply. This Tg is for the resulting copolymer or the blend, miscible blend, which is given by W1 Tg1 plus W2 Tg2. Tg1 is the Tg for the component 1, W1 is the weight fraction. Similarly, W2 is the weight fraction for component 2 and Tg2 is the weight fraction for the second component. Now, this equation gives linear or straight line variation, linear variation with composition. So, if you vary composition, you get linear variation by this equation. Now, this generally overestimates the Tg of the copolymers or blends slightly, overestimates slightly. So, the other equations used are given by this 1 by Tg W1 by Tg1 plus W2 by Tg2. Again the terms are same. Remember this T, these Tg's are in Kelvin. are in Kelvin. So, do not confuse that. For applying these equations, you must take the temperature in Kelvin. Now, this case, obviously this equation predicts the curve below the straight line with composition. So, if you have a straight line here, it will have little curve below that, and is typically underestimates, is basically underestimates little bit about the Tg's for the miscible blends or the copolymer. Hence, the actual Tg lies between a Tg which is somewhere between predicted by these two expression. Now, obviously, if these two blocks in a block copolymers or say two homopolymers in blends are partially miscible, then what happens? You still gets two Tg's for a two component system, but the Tg's comes down from the corresponding homopolymers, you get somewhere intermediate. So, basically, if you find out or if you measure the Tg's or if you do a differential thermal calorimetry, which we will just talk in a minute, you will find depending on how many Tg's you are getting, you can estimate or you can predict or you can know whether the blends are miscible blend or they are partially miscible blend or they are completely immiscible blend. Similarly, you can find this whether blocks, the two blocks in a block copolymer are miscible or partially miscible or completely immiscible. So, if you want to show this in pictorially, if you have a two phase system, immiscible system, you get corresponding two Tg's corresponding to the homopolymers, and if you have completely mixed or miscible blend or miscible copolymers, then you have a Tg intermediate between these two. The value of this Tg is given by the two expression I just wrote in a minute. We will come to Tm and melting point. Before coming to melting point discussion, let us just recap the crystallinity in polymers, which we discussed in length in the last lecture. Crystallinity in polymers, as you know, as we discussed many times in this course, that polymers are hardly crystallized up to 100%. So, most cases if the crystallinity varies from 0 to 100% in a polymer. So, polymers are generally semi crystalline in nature, and you have a non equilibrium microstructure coexisting the amorphous and crystalline region. We talk about non equilibrium because when we introduce crystallinity in the polymers, the amount and the nature of crystallinity depends upon how you are introducing the crystallinity, whether you fast or you slow. So, the microstructure you get consisting of amorphous and crystalline region are basically non equilibrium structure, and that microstructure actually determine eventually the properties of the material. We also discussed requirement for crystallization. Basically, the polymer chains has to have a regular molecular structure, so that the chains can pack close to each other easily, and obviously, if the intermolecular force between the polymer chains are higher, then they can pack easily or they remain packed easily with each other. So, these are the two criteria must be fulfilled, so to get a crystalline polymers. How do you induce crystallinity in a polymer material? Remember, we discussed last class that generally we can introduce by cooling a molten polymer or annealing a semi crystalline or amorphous polymer at a specific temperature. Annealing is just keeping a amorphous or semi crystalline polymer at a particular temperature for a long time. You can introduce crystallinity by evaporating a polymer solution slowly and the another way we can induce crystallization by drawing, which basically means stretching the polymer strands or polymer chains at a particular temperature above Tg, by which they can align and then crystallize with each other. So, what are the factors that influence the value of melting point or melting temperature? Let us think about the thermodynamics little bit. We know that say if we consider delta G of melting, delta G of a process, we can write T del S m. Now, these are the delta G m, delta G, delta H m and delta S are the corresponding terms for particular repeat unit, per repeat unit. Now, at equilibrium, which is a case of melting. So, at melting delta G m would be 0, T is T m melting point, hence T m is given by delta H m delta S m. Let me write it one again, delta m by delta S m. Delta H m is melting is always endothermic process. So, this is a positive value. Similarly, entropy change in melting process result in increase in mobility of the polymer chains. So, the entropy goes up. So, if you from this expression, if you can increase the value of T m either by increasing the value of del H and by decreasing the del S value. If del H can be increased by improving the intermolecular attraction, if you increase the intermolecular attraction between the polymer chains, then obviously the delta H of melting goes up. And similarly, if the entropy del S term can be reduced, then the Tg goes up. We will discuss the specific example in a minute now. So, this is what I discussed, that delta G m is delta H m minus T delta S, delta m delta S are enthalpy and entropy of fusion or melting per repeat unit, and at equilibrium delta G m 0. So, this is 0. So, to increase T m, we increase chain stiffness or mobility. If we increase chain stiffness, if we increase the chain stiffness, what happened? When we melt these polymers, if they are stiff, if the polymer is stiff, then the increase in entropy is not much. Obviously, if you have more flexible chain, then to bring the chains from a close packing to a molten state where the polymers have much more mobility. If the polymers are intrinsically more flexible, obviously for a flexible polymer on melting, delta S goes up more than a polymer chains which are much stiffer. So, to increase T m, you prefer to have a stiffer chain, because if you have a stiffer chain, the entropy increase on melting is less. So, T m goes up. Similarly, you can increase the intermolecular attraction, you can introduce some specific bondings like hydrogen bonding that will increase the enthalpy, delta H of melting, and by that we can increase the melting point. And obviously, better packing is always help in increasing the, you can understand better packing is always improve the Tm melting point of the polymer. So, what are the, if you look at a chain microstructure or chain chemical structure, what are the factors you can we can think of which will affect the value of Tm? Obviously, we discussed backbone stiffness. Now, I will give few examples so that we can verify this concept. So, let us talk about first these example. Polyethylene have Tm around 137 to 146 degrees. If you introduce a flexible group in the backbone, then flexibility goes up. So, delta is goes up. So, your Tm goes down. So, it comes around 122. If you just have a ether linkage, then flexibility goes up even higher, you get a drop in Tm value. If you introduced a phenyl rake in the backbone, your stiffness will go up and you get a much higher Tm value, increased Tm value as a result of increase in the backbone polymer chain stiffness. We can give more example of backbone stiffness. For example, if we consider these polyesters, when R is CH2,4, CH2,4 is linear normal alkane, which gives us a very flexible chain, and the Tm is 50 degree centigrade. If we increase much stiffer molecule back group. So, we are giving example of this backbone stiffness, which will affect the value of Tm. So, if you have a much stiffer backbone, by introducing a rigid phenyl group, the Tm goes up to 70 degree centigrade. If you have more stiffer group, Tm goes up even higher. If you introduce a flexible group in between, then Tm goes down, whereas instead of CH2 CH2, if you have a olefin group which makes the chain even stiffer, then your Tm goes up drastically. So, the example we have seen in this page and in this page confirms the understanding that if we increase the backbone stiffness, the Tm goes up. Now, let us talk about the second factor, polarity. Let us have some example about polyamides. So, if you have more flexible group instead of CH2, for example, 3 groups, 3 CH2 groups, then the polymer becomes, the contribution from this CONH2 group in this case is higher compared to this case, because you are adding more non-polar groups. Hence, the intermolecular attraction goes down, hence the Tm goes down. So, 260 degree. If you increase further, then Tm goes down further. Now, in this case you can argue that this drop in Tm could be because of the increasing flexibility of the backbone, but you are right, it can cause some decrease in the Tm because of the increased flexibility, but the amount of drop shown here, that can be only explained by the decrease in the intermolecular attraction because of the fraction of CONH group is less in this polymer chain compared to the one shown here. Similarly, you can compare nylon 66 265 and nylon 610 222. Here also, because you have, for a given molecular weight, you have less number of CONH group, the Tm goes down. The third factor we can think of is backbone symmetry or and pendant group regularity. If we consider this example, when X is H, that means polyethylene, Tm is 137 to 146 degree. When this is CH3, if you have CH3 group, the polymer chain becomes more stiffer, hence the Tg goes up. But if you increase the length of the side chain, as we have seen in case of Tg as well, that the chain rotation is mainly determined by first 1 or 2 pendant groups. If you have longer pendant groups, it actually plasticizes the polymer molecules by increasing the free volume. So, if you increase the pendant group, what happened? It increased the free volume, hence the flexibility goes up, and as a result your Tm goes down. So, if you increase further, your Tm further goes down. However, if you have same thing we have seen for Tgs, in case of Tg, if you have bulky side group, not a long pending group from the chains, but if you have a bulky groups, then this contributes or gives steric hindrance in rotation, and which increases stiffness, where in this case it free volume increases and flexibility of the polymer chain increases because of the increase in free volume. So, in this case the stiffness goes up, and as a result the Tm goes up, and if you have even bulkier group, even bulkier group, then the Tm goes up further. So, it is basically the pendant group which, so it is basically we are talking about pendant group size, we are not talking about this. So, we are talking about pendant group size and type. So, depending on what is the type and size of the pendant group, the melting point get influenced. If we compare, give one example here. Not this one, let me find. Okay, so let us go back and look at this slide. We have discussed the backbone stiffness, we have discussed the polarity, we have discussed the effect of pendant group size and type. Obviously, if we have branches present in the polymer chain, it hinders in crystallization. So, crystallization becomes difficult. So, it affects the Tm, and if you have pendant polar groups, then it affects, or if you have pendant polar groups, obviously the intermolecular attraction goes up, and as a result Tm will go up. If you have pendant groups present or the substituents present regularly, then it is easy to pack, or packing becomes better. So, Tm goes up. If the pendant groups are not placed symmetrically, then the Tm goes down. So, as a general factor, we can say that only linear polymers can form crystals. If there are branches present in the polymer chain, it does not form crystals or does not crystallizes. Stereoregularity in a polymer molecule is critical. So, a syndiatactic or isotactic polymer will have better crystallability than atactic polymers. Copolymers are, we are talking about random copolymers, where if they are due to their molecular irregularity they rarely form crystal, and obviously, so if you cool the polymer melt slowly, then the polymer chain gets more time, and they can crystallize, and the crystallization take place easily, or the crystallites can grow in a bigger size. Molecular also influence the value of Tm. This because, as we have seen in case of Tg as well, that if we the chain ends are having much more free volume. So, end of the polymer chains are much more flexible. So, if you have a shorter chain, then the polymer is effectively more flexible, Tm goes down, and if you have a higher chain, the contribution from the ends is less. So, Tm goes up. So, this is one example of normal alkanes has shown that with increasing the chain length, number of carbon atoms, the Tm value goes up, and eventually it's become a steady value. So, if you want to compare between two polymer chains, it's preferably to compare in high molecular weight, so that the Tm is almost independent of the molecular weight. Now, we discuss the concept of Tg and Tm, and we also discuss the chemical, how the Tg and Tm depend on the chemical structure of a polymer chain. Now, we will move and briefly discussed how we determine or measure Tg and Tm in laboratory. We have discussed this that there are lots of physical properties changes during the glass transition and melting. Some of them are listed here: specific volume changes, specific heat capacity, refractive index, modulus, heat conductivity. There are many others which can list, but these are some of the examples. Some of the physical properties undergo change their value during glass transition and melting. So, if you can follow any of this property with temperature, we can find out the glass transition temperature and melting point. The most basic techniques which are used in laboratory for determining Tg and Tm are DSC and DTA. DSC is differential scanning calorimetry and differential thermal analysis. So, DSC stands for differential scanning calorimetry and differential DTA stands for differential thermal analysis. What is the principle of DSC and DTA? In DSC, you typically have a chamber where a sample is placed. So, that is your sample S, and you have a reference which is empty. There is a heater, so sample heater, ES supplies energy. There is a thermocouple, sample thermocouple TS. Similarly, here you have a reference heater and you have reference thermocouple which determines the temperature. Thermocouples determines the temperature of sample and TR thermocouple determine the temperature of the reference. There is a gas inlet. Typically, we do experiments in inner atmospheric. So, there is a gas inlet and a gas outlet. So, what is done in this experiment? The sample and reference, which is just a blank, samples are typically taken in aluminum container, and then the aluminum container can be covered and crimped, so that nothing goes out from the container, and parallelly there is a blank container without sample is kept. These two are heated and the temperatures are maintained same. The temperatures for this sample and the reference are kept maintained same, and to maintain the same temperature, the heat or energy is supplied to the sample. If there is something happening, some exothermic or endothermic reaction going on. So, if there is some exothermic transition or reaction happened here, then to maintain the temperature, the system has to supply more energy from outside to maintain the temperature. So, basically in this case, energy supplied is plotted against temperature. If there is a endothermic process goes on in the sample, then you have to supply energy from outside. If some exothermic process goes on, then heat evolves in the samples. So, to maintain the same temperature between sample and reference, you have to take out some energy. So, delta E becomes negative. So, if you consider a process, typically what happened, there is always delta is never is 0, because there is always a difference in the heat capacity between the sample and the reference. So, you have to always supply more heat, or at least different amount of heat, higher heat energy, to keep the sample at the same temperature as the reference. So, delta is always positive, never not equal to 0, due to difference in heat capacity of sample and the reference. To keep, so this again, this delta is the amount of energy or the heat you have to supply to the sample to keep the sample and the reference temperature same. So, delta E will be proportional to the difference in the heat capacities between the sample, heat capacity of the sample and heat capacity of the reference. So, if there is no change in heat capacity of the sample, then the value of del E will remain same, which will give us the baseline. So, if we start, del E will start somewhere and remain same as long as the heat capacity of the sample remains same. Now, say the sample is undergoing glass transition temperature. If sample goes glass transition temperature, which is a endothermic process, so the system has to supply more energy. So, delta E will be higher, and then once the glass transitions is over, then it will be same, again remain constant, because the heat capacity of the rubbery state is higher, typically higher than the glassy state. The delta E value will be higher in rubbery state corresponding to or compared to a glassy state, and this difference will give the delta Cp between the glassy state and the rubbery state. Now, this, if we increase further, the temperature now, if you continuing heating, a time will come when this polymer sample will undergo melting, and you get a peak corresponding to the melting point of the polymer. So, you get a curve like this. In case of DTA, differential thermal analysis, a similar concept is applied, where you have a chamber which has a inbuilt heater, this is a heater and you have a sample, and again you have a reference. You have a thermocouple for the sample, a thermocouple for the reference. There is a place to put the gas inside, and there is a gas outlet is also there. So, in this case what happened, heat is supplied at a particular rate in the system, and the difference in the temperature between the sample and the reference is observed. So, in this case delta T is the temperature difference between the sample and the reference is plotted against the temperature. So, if there is a exothermic process, delta T will be higher as a result of increase in heat inside the sample. If there is a endothermic process, there will be delta T will be lower correspondence to the reference, because you are supplying constant amount of energy to the system. So, if we plot the same graph like we did for DSC, we get a dip at Tg, glass transition temperature, and melting peak, you get a exo peak. So, this is Tg and Tm. So, in case of DSC, the temperature between the reference and the sample is kept constant and the required energy is supplied. So, delta E is the amount of energy required to keep the temperature between the sample and reference same, is plotted against T, and in case of DTA, differential thermal analysis, the same amount of heat is supplied to sample and reference at a constant rate, and the difference in the temperature between the sample and the reference is plotted against the temperature. So, any phase change which involves any glass transition or melting, which is endothermic process, will require more heat to maintain the temperature, and ideally this should be a sharp increase here, but as all of us know that the polymer sample consists of many chains of different length. So, the Tg corresponding to each chains are different. So, that is why we get a broad nature of this transition, because each higher size polymers will have slightly higher Tg correspondence to compared to a polymer chain having lower size. Similarly, the Tm is little less sharp compared to a small molecular melting point, because the polymer chain has many molecular weight, basically consist of chains having many molecular weights. Now, this Tg, when you talk about this DSC, how the Tg is obtained mathematically? If we draw this portion again, we can, so that is endo. So, different scientists use different techniques to find out the Tg. Some uses this inflection point, the inflection point as Tg, many uses, or that is the most used technique, where there is a inflection point here and there is a inflection point here. The midpoint of these two, the midpoint, some people consider this as a Tg, and some cases what happened, the point where there is a maximum change in the slope during this entire temperature, the slope changes, keep on changing. So, the point where the maximum change in slope happens, some people consider that as a Tg. Now, this and this is very close to the midpoint of this changeover. So, generally if nothing is mentioned, we assume that the Tg is the midpoint of these two inflection point. From the melting point peak, from the area, from this area we can get the enthalpy of mixing from the area of this melting peak, and if we know the enthalpy of perfectly crystalline material, perfectly crystalline polymer, then from this value and the value from of a perfectly crystalline same polymer, we can get the percentage crystallinity in our sample. So, this is how we can apply DSC and DTA to find out the Tg and Tm of a polymer material. Now, typically what happened, if we want to find out Tg precisely, generally in a semi crystalline material, the Tg, the amorphous regions are in between the crystalline regions. So, what is the practice we do is basically quench cool. If we take the polymer, melt it at a higher temperature and melt it and then cool it quickly so that there is no crystalline regions formed or less crystallinity obtained. So, and then reheat to find out the Tg of the material, then we get a proper peak for the glass transition. If we have a crystallizable material and we quench cool and then reheat, what happened after the Tg, sometimes if the rate of heating is slower, then it can crystallize. So, this is corresponding to crystallization. So, there is a exothermic process. So, this is a exothermic peak and this is called cold crystallization. Remember, this happens if we quench cool a crystallizable polymer to a lower temperature below Tg, so that it was supposed to crystallize, but it could not crystallize because of fast cooling. Then if we reheat at a particular temperature, it start crystallizing. So, this temperature is called cold crystallization temperature, not Tc. Just quickly before we wrap up this discussion about this topic, now Tg and Tm are quite related, and typically for homopolymers, Tg lies between 0.5 Tm .5 Tm. So, basically Tg and Tm are not independent for homopolymers. So, you cannot vary the Tg and Tm independently for homopolymers. They are quite related, as we have seen from the structure property relationship between Tg and Tm. So, with this we conclude our discussion on the amorphous and crystalline state of polymeric material, and our discussion on Tg and Tm. And in next class next lecture we will continue. If something is remaining, we will continue the discussion, but mostly we have covered the discussion on amorphous and crystalline state.